Okay, we continue our study in graph theory today by talking about what we call Euler and Hamiltonian paths and circuits. We're going to start with Euler paths and circuits. We talked a little bit about how Euler is a mathematician from the 18th century, and we talked a little bit about that problem that he was able to prove, the Königsberg problem with the 7 bridges. He was able to prove that there was no solution for that. So this is going to relate back to that problem. Okay, so an Euler path is a path that uses every edge in a graph with no repeats. So last time we talked about a path being just going from one vertex to the other without reusing an edge. But we didn't have to use every edge. But an Euler path is a particular type of path where you do use every edge in a graph with no repeats. So you use exactly every edge exactly once. Now, it does not have to return to the starting vertex as long as you use every edge in the graph. An Euler circuit, on the other hand, so we talked about circuits being a path that goes back to where it started with. Now, an Euler circuit is a circuit that uses every edge of a graph with no repeats. So this must start and end at the same vertex. Okay, so let's take a look at an example. So we're going to determine whether this first one is an Euler path and whether that second one is an Euler circuit. Okay, so for this first one, is this an Euler path? So in other words, can you find a path where you go and use every edge, but you only use every edge once? So this, when you're first starting to look at it, might take a little bit of time. You can go back to a vertex as long as you do not use the same edge to get back to that vertex. Okay? So let's see, in this case, if we start at A, we go to B, and then from there we go to C. Okay. Now from C we can only go to D. From D we have a couple of places, a couple of options, but let's see if we can finish up the edges up on the top first before we go to the bottom. So let's go back to B here. And then from B, we have to go through to E. And then from E, again, a couple options, but we need to go through and make sure that we aren't going to reuse an edge. So it looks like we'd have to go to D, and then from D to F, and then from F to E, and then from E to G. So there is an Euler path here. So we would write down exactly which vertices we go through to indicate the path. So A, B, C, D, B, E, D, F, E, G. And we would say, yes, this is an Euler path because we were able to use every edge exactly once. Okay, for the second one here, is this an Euler circuit? So remember, an Euler circuit, you are using every edge exactly once, and you are going to start and end at the same vertex. Now, this might take a little bit of trying to think about where you want to start and where you want to end. Obviously, they have to be in the same place, but there could be multiple ways of doing this. We can start at A again, just to see if we can find something. So if we start at A, let's go to B. And from here, let's see, we'll try to use up all the edges that are up at the top first. So let's go back to A, use that edge. And then let's go from here, let's go to C. Okay, from there, we only have one option to go to D. And remember, we need to go back to A at the very end. So here, we definitely don't want to go back to A just yet because we haven't gone through every edge. So from here, we can go from D to B, to F, to E, back to D, and then back up to A. Okay, so there's one example of an Euler circuit. Another example would be if you started at D, you could also come up with an Euler circuit as well. So with that, you would go from D to B to F, then E, then D, up to A, over to B, to A, to C, and then back to D. So that's another example of an Euler circuit. But as long as you find one, then you're able to say that this is an Euler circuit. Now, what's nice about Euler paths and circuits is that there are actually theorems that go along with them. So what I mean by theorems is there's going to be an easier way, there's going to be a rule rather than just kind of guessing and checking and trying to find an answer. There's a theorem that will allow us to determine whether or not something has an Euler path or an Euler circuit without needing to come up with that path or that circuit. So here they are. So the first theorem is a graph will contain an Euler path if it contains at most two vertices of odd degree. Okay, a graph will contain an Euler path if it contains at most two vertices of odd degree. So what this means is if all the vertices have even degree, then definitely have an Euler path. If it has, so if at most two vertices of odd degree. So if there are two vertices that have an odd degree, that's fine too, you'll have an Euler path. But once it's more than that, if you have 3 or 4 vertices of odd degree, then you can say for certain that the graph will not contain an Euler path. Okay, so no more than 2 vertices of odd degree. If it's more than that, there is no Euler path. Now what about for an Euler circuit? Now a graph will contain an Euler circuit if all vertices have even degrees. So if there's even one odd degree vertex, you can say for certain that it will not be an Euler circuit. But if they're all even, you know right away, there's an Euler circuit. Even if you don't have the path written out, you'll be able to say that there is an Euler circuit. So in example 2 here, we are going to determine whether each graph is an Euler path, an Euler circuit, or neither. So let's start with this first one here. What we're going to do is we are going to determine this by just looking at the vertices and looking at the degree of each vertex and determining from there if there is an Euler path, an Euler circuit, or neither. So for this first one, let's go ahead and draw ourselves a chart. And we are going to list off all 4 vertices, and we're going to fill out what the degree is. So vertex A has degree 3, because there are, as a reminder, to figure out the degree, you're looking at how many edges are coming into that vertex. Okay, so that's 3. And then vertex B, 1, 2, 3, 4. C also has 4. And D has 3. Now because we have 2 odd degrees, we can say that this has an Euler path because, well, it definitely can't be an Euler circuit because they would all have to be even. But this does have an Euler path because there are only 2 odd degrees, no more than that. Okay, so that is an Euler path. We'll do the same thing with the second one here. So for each vertex, we'll list off the degree. So A has degree 2, B degree 4, C is 4, D is 4, and E is 4. So in this case, you can see that all the degrees are even, which must mean that this is an Euler circuit. Okay, and then for the third one, again, we'll do the same thing. You should recognize this graph. This is from the 7 Bridges of Königsberg problem that we looked at last time. And we are going to, again, list off the degrees. So vertex A has degree 3, B, 1, 2, 3, 4, 5, C has 3, and D has 3. So you'll notice in this that there are more than 2 odd degrees, so we can say it's neither. Now this goes back to last class where we were talking about this problem, and we said that Euler was actually able to prove that there was no way of going through each bridge once and only once without repeating one of those edges. So that's how he came up with these theorems, that once there are more than 2 odd degrees, that there is no way to come up with, well, what is now named after him, an Euler path. And so this is a little bit of a look into how he was able to prove that. Obviously, we're not going to go through as thoroughly his entire proof, but his proof that this problem didn't work allowed him to come up with these rules, these theorems that we can now use to easily figure out whether or not something is an Euler path or an Euler circuit or neither, without actually having to try it until you give up. Okay, so we talked about Euler paths and Euler circuits. Now we're going to move into what we call Hamiltonian paths and circuits. So a Hamiltonian path is a path that visits every vertex once with no repeats. Now this is different from when we talked about Euler paths and circuits, because in Euler paths and circuits we were talking about the edges, right? So a path that would go through every edge exactly once. But in some of those cases you would visit a vertex more than once. Hamiltonian paths have to do with the vertices. Okay, now for a Hamiltonian path, because it is a path, it does not have to start and end at the same vertex. On the other hand, a Hamiltonian circuit, which is a circuit that visits every vertex once with no repeats, this one must start and end at the same vertex. Now, unlike Euler paths and circuits, which were nice in that there were theorems, Hamiltonian paths and circuits don't have any theorems that allow us to instantly determine whether or not that circuit exists for all graphs. What was nice about those theorems for Euler paths and circuits was you didn't have to come up with the path. You didn't have to come up with the circuit. You didn't have to try. You just had to come up with the degrees, and once you look at the degrees, you can instantly say, oh, there is an Euler path, or this is an Euler circuit. But with Hamiltonian paths and Hamiltonian circuits, there is no way to go about determining that. But there are ways of going about explaining when, for example, you could say that there is no Hamiltonian path in a particular example, and you can come up with an explanation of why. But there's no theorem for us to use that allows us to just say, if this, then you know for sure, without having to kind of try for yourself until you find a solution. Okay, so in example 3, the first one there, determine if a Hamiltonian path or circuit exists in each of the following. Okay, so let's start off with a Hamiltonian circuit. So this is going to each vertex without repeating any vertices. Now, in terms of the edges, you don't have to use all of them. The point is you want to get to each vertex. So if we started here at B, and then we could go up to A, then down to C, then over to D, and then over to E. Okay, but in terms of a circuit, what happens here? Well, anytime you get to E, there is no way to get to another vertex without going back to D, right? So in terms of a Hamiltonian circuit, we can say that it's not possible because there's no way for us to leave vertex E without going back to D. And by going back to D, then you would be going back to a vertex you've already been to, right? Because going through D is the only way to get to E, but in order to get from E back to something else, the only way is through D. Okay, so that's kind of an example of how we would have to explain without having a theorem, right? So you can explain that, but there's no theorem that says, oh, if this, then this. Now, in terms of Hamiltonian path, well, we just found one, right? It went to every vertex without repeating. Now, the key here is, because you know that there's no possible way of leaving E without going back to D, you either have to start or end with E for your path in order for this to work. So no matter which path you end up finding that's a Hamiltonian path, it's going to either start or end with E, right? So you could say A, B, C, D, E works. You could say E, D, C, A, B works. E, D, C, B, A works. But all of those either start or end with E. Okay, for the second one, let's go ahead and see if we can find a Hamiltonian circuit. So let's say we start at A, then we can go over to B. Let's see. Now from here, this might just take a little bit of guesswork and trial and error. Let's say we went to F. Okay, so from F, we can either go over to E or down to G. I think if we go down to G, it might help us get to everything on the bottom. And then let's cover all these vertices that are on the bottom. So let's see, we can go to C from here, then over to D. Let's go up to H, then I, and then E, and then now we can go back to A. Right, so there is a Hamiltonian circuit here. And in terms of a Hamiltonian path, well, we can either say, well, just don't go back to A, right? From A all the way up to E, that works. We can also see if there are any other Hamiltonian paths if you didn't start at A, going from A over to B. Let's say you went from A and then went down to D. And then from D, we can go over to C, kind of go around the outside first, then up to B. Then let's do the inside, then we go to F, then E, then I, then H, then G. So that covers every single vertex. We didn't repeat any vertices, so there is a Hamiltonian path as well. So this had both a Hamiltonian circuit and a Hamiltonian path. Okay, so main takeaways from today: Euler paths and circuits are talking about going through every edge. Hamiltonian paths or circuits talk about going through each vertex. And for Euler paths and circuits, there are two theorems that you can use to instantly figure out whether or not an Euler path or circuit exists. But with a Hamiltonian path or circuit, there are no theorems. You do have to just try and try some possibilities until you can determine whether or not there's any. But if there isn't any, there is still a way to explain why there is no possible circuit or why there is no possible path.